Okay, so I'm going to solve some problem off this chapter 6 on columns, and we're going to do first problem 1. It says a column has both ends pinned and has a length of 32 inches. It's made of SA1040 hot rolled steel, circular shape with a diameter of 0.75 inches. Determine the critical load, PCR. Alright, so a summary of the information given. So we have the length of the column, 32 inches, the material, SA1040. We're going to find from the back of the book what the modulus of elasticity is. It's round, 0.75 inches. If it's pinned at both ends, then the end fixity coefficient is 1. Okay, so yeah, we're going to use Young's modulus, and also we're going to need for this material, so 1040 hot rolled, Young's modulus. It's a footnote on page 788. Modulus of elasticity 30 times 10 to the power 6 psi. And also we need yield strength if it's the case of a plastic buckling using Johnson's theory. So from the table we have yield strength 42 ksi. 42 ksi. Okay. All right, so this is the information about the material. We're going to use follow the flow chart on page 224, and we need to compute the column constant. Column constant is 2 pi squared times modulus of elasticity over yield strength at power 1 over 2. Okay, so let's calculate this. So I said 2 pi squared, 2 times pi squared times 30 exponent 6 over 42. And we need to take psi because E is in psi, so 32 exponent 3 equals, and then square root. And column constant is 108.7. We need to calculate slenderness ratio. So we have effective length is K times L, and that's L because K is 1, so we have it 32 inches. To calculate the slenderness ratio, we have a symbol for it. It's SR. Let's see, SR, yes. Effective length over minimum radius of gyration. So slenderness ratio is effective length over radius of gyration. Now, radius of gyration for solid round is, go to the back of the book, so it's solid round, it's R is d over 4. It's a bit misleading, so we read R as d over 4, you think R is the radius, but that's radius of gyration. So we have 32 inches over diameter over 4, that's 0.75 over 4. Okay, so let's calculate this quickly. 32 times 4 over 0.75. It's 170.7. Okay, so one more time, 32 times 4 over 0.75 indeed. So what we're seeing is that the slenderness ratio, so slenderness ratio is greater than column constant. It means that it's Euler buckling or elastic, and not due to plastic deformation. So the critical load equation on the ES branch of the on the flow chart is going to be pi squared Young's modulus times moment of inertia over effective length squared. Okay, so we have pi times 30 times 10 to the power 6 times. Also need we need Young's area moment of inertia. So we're going back to the appendix with the shapes, and that's appendix 1. So it's pi diameter power 4 over 64. So pi diameter of power 4 over 64. Okay. I'm going to just plug it here. So again, pi, and this was squared. Almost missed it. So pi Young's modulus, and then pi again. Diameter is 0.75 at power 4 over 64 over effective length is 32 inches, and this gets squared. Okay, so let's see. We have pi power 3 pi at power 3 times 30 exponent 6 times 0.75 at power 4 over 64 over 32 squared equals, this is 4,491 pounds. Okay, so this is the answer to this problem. It says repeat problem. Let's also do this one. Repeat problem 1 using a length of 15 inches. So less than half. How is this going to change? Let me use color. So instead of 32, we have 15. And 15, this equation, repeating, calculating the slenderness ratio. Column constant stays the same. So 15 times 4 over 0.75, and this is 80. So we're having the 80 is less than, so now we have 80, and column constant is 118.7, so this is Johnson. Parabola, or Johnson's that is plastic buckling. Same flow chart has systematically here, easy to follow. So for this case, so problem 2 now, the critical load is going to be area times yield strength, and then 1 negative yield strength times effective length over R. That's the slenderness ratio. So we have it, slenderness ratio at power 2 over 4 pi squared times E. Okay, so let's calculate the area now. It is going to be pi diameter squared over 4, and with the 0.75 diameter, so pi times 0.75 squared equals, that's 0.4418 inches squared. Okay, so I have the area 0.4418 times yield strength. We need to match the strength value with inside and outside parentheses. So it's going to be 30 times 10 to the power 6, and then 1 negative 30 times 10 to the power 6 times the slenderness ratio was 80, and it's squared over 4 pi squared times I think I have so yield strength. I'm sorry, this was supposed to be mistake. So this is 30 times 10 to the power 6, while this one is 42 times 10 to the power 3, and this is 42 times 10 to the power 3. Okay. All right, so I have the area, and then times 42 exponent 3, and then times parentheses 1 negative 42 exponent 3 times 80 squared over 4 over pi squared over 30 exponent 6 close parentheses equals. So I've got critical load, and before writing the number down, definitely we expect a value that is bigger than the for the case of a slender, the slender column with 32 inch long length. So I have 14,344, we could say, pound. Okay. So these were problems 1 and 2. You saw me, I just followed the flow chart. I said it before, essential is to recognize the type of n-fixity coefficients. Okay. So this was one recording. All right. Back to solving problems. This one is so problem 1. It says, repeat problem 1. If the column has an initial crookedness of 0.0 inches, determine the allowable load for a design factor of 3. Okay, so we have the information, from solving problem 1, what is in black, and we're going to consider the case where the column has some crookedness. So problem 623. All right, and so crooked column, page 232. We're going to utilize this equation here. So design factor is given, again, A, it's the initial crookedness, and then we have C, This is going to be the, looking at the figure, is going to be the radius of the bar, or half the diameter. So it's diameter over 2, and 0.75 over 2 inches. That's 0.375 inches. Okay. And then text of the problem, if you go in the so crookedness 0.08 inches. Okay. And so yeah, and what else? Design factor N equals 3. So we need to calculate the allowable load, and this is the equation to use. And so it will be a quadratic, and we're going to select, of the 2 possible solutions, select the smallest. Okay, so the quadratic is of the form PA squared plus C1 PA admissible load plus C2 equals 0. C1 is going to be negative 1 over N yield strength times area plus 1 plus crookedness times distance from the neutral axis to the outside of the bend, R squared. Okay, and then times critical load from Euler analysis, and then the C2 coefficient is going to be yield strength times area times critical load from Euler analysis, N squared. Okay, so negative 1 over 3, and we have the yield strength 42 ksi. And this one, so let's see what kind of units we have. We have area. All right, so we're going to use psi. So 42 psi times 10, 40 times 10 to the power 3 psi times area. We have area calculated is 0.4418, and then plus 1 plus A is 0.08, and then C again was half the diameter, 375, and then we have radius of gyration. We had that calculated too. That's the radius of gyration, 75 divided by 4. So 0.1875. Okay, and then times the critical load from Euler. That's 4,491, 404,091. Okay, and then the other coefficient, C2, we have 42 times 10 to the power 3 times 0.4418 times critical load 4,491 over 3 squared. Okay. So let's calculate this one first. C2 first. So I have 42 exponent 3 times 0.4418 times 4491 over 9 equals. So this is 9,250, rather 9259244.4. Okay, and the other one, so I have 42 exponent 3 times 0.4418 plus parentheses 1 plus 0.08 times 0.375 over 0.1875. Okay, so equals, and need to start over. So 1 over 3 times parentheses 42 exponent 3 times 0.418 plus parentheses 1 plus 0.08 times 0.375 over 0.1875 close parenthesis times, forgot to multiply by this apparently earlier, 91 close parenthesis equals, so this is negative 7921.7. Okay, so the allowable load according to this equation is going to be 0.5 times negative C1 plus minus solution to a quadratic C1 squared minus 4C2. Okay. So let's calculate this first. Discriminant. I have C1 7921.7 negative, doesn't matter because it's squared, negative 4 times 9259244.4 equals, take the square root, so this is 5071.1. Okay. Alright, so the two values now, and we're picking the smallest, there will be, and C1 again is, so I have negative, and with negative is positive, so I have 7921.7 plus the discriminant equals, divided by 2 or times 0.5, this is 6496.4 pounds. It's a bigger value than the case with no crookedness, so this is not going to be the clearly the second calculated value with minus is going to be the smaller value. And as I said, we're anticipating a value that is less than the perfectly straight column. All right, so again, negative, negative, so it's positive 7921.7, negative, the discriminant equals, divided by 2 equals, and this is 1,425.3 pounds. So this is the answer. Okay. All right. So we've got problem 23 solved, and I'm stopping here.